Okay. Can you see a PPT? Can you see a PPT file? Can you all see a PPT file?
No, ma'am. Oh, yes, ma'am.
No, ma'am. No, ma'am.
I'll reshare the screen. Okay. Now can you see the PPT?
Yes, ma'am. Visible.
Mechanics, vector algebra, and vector calculus written. Okay. So this is what we'll be doing, vector algebra and vector calculus. Although this is for CC1, as I told you, but we are doing the same thing for G2. We believe in certain bits, but mostly it will be a general discussion on vector algebra and the primary things, concepts that we other parts of okay. So we start by asking someone is on unmute, because I think we have already started recording the. So first we'll ask the question: how do we define a vector? Okay. Can someone tell me how we define a vector? How is a vector defined?
A vector is something which has both magnitude and direction.
Okay, it is something which has both magnitude and direction. All right. So a physical quantity that has both magnitude and direction is called a vector. All right. But now that you are a little further in your sort of what should I say, academic life than your class 2, so we'll add something more to this apart from what we already know. Okay. So we ask this question whether electric current. Now we all know that how does electric current go from one point to another? We know that when there is a difference in potential in the conductor. And someone has, please, someone is unmute. Please mute yourself. You know, this noise, when you are unmute, even if you're not talking, there are noises that are coming and that disturbs a lot. So please mute yourself. So we know that an electric current takes place when there is a difference in potential between 2 points. So when there is, what is the difference in potential? When there are more electrons at a point and there are lesser electrons at another point. So electrons always try to equalize the amount. Charge always seeks equality. But in general, when they are in an insulator, they cannot flow. However, if it is a conductor, then electrons are free to move. So if there are more electrons at one point and less electrons at one point, it means that one point has more negative charge and the other point has less negative charge. Then electrons flow from the points where there are more negative charges to the points where there are less negative charges to equalize the number of negative charges. Now, by convention, we say the points with more negative charges to be the negative potential and the points with less negative charges to be the positive potential, right? And we say current moves from the positive potential to the negative potential, that is from higher potential to lower potential. And this is similar to flow of heat, flow of water, all right? So what I'm trying to, now you might think that we are discussing vectors. Why are we discussing currents in this? What is the context? See, why we are, I'm bringing up this point is that when current flows from one point to another, there is a specific direction in which it flows, right? Current always flows from the point at positive potential to the point at negative potential. Electrons flow the other way, but by convention it was taken that current flows from higher to lower potential. So current always flows in a certain specific direction. Current will never flow just in any haphazard direction. It will always flow from the point at higher potential to the point at lower potential. So it definitely has a direction. But do we represent electric current by a vector? No, we don't, right? Electric current is simply rate of change of flow of charge. So limit delta T tends to 0. If delta Q amount of charge flows in time delta T, then limit delta T tends to 0. Delta Q by delta T, which is represented as dQ dt, is current. So current is basically charge per unit time. So there is no question of a vector here, right? We do not give a vector sign to current, but definitely the charges move in a particular direction. Okay. So why cannot current be called a vector? Can someone give me the answer? Why do we not call current a vector, although it definitely flows in a certain direction and not in any random direction? Still, why can't we call it a vector? Okay, I'll give you the answer. Because now we will give a new definition of vector. From our old definition of vector, which someone just said, that it is a physical quantity which has both magnitude and direction. If we stick to this definition of vector, then we might as well call current a vector because it always has a magnitude and it always moves in a certain direction. But now we will add another point to the definition of vector. Physical quantities that have both magnitude and direction and obey the laws of vector addition. So this third point was not there earlier. If you recall the laws of vector addition, then we can add vectors using the triangle law, using the parallelogram law. We will discuss these laws in a few minutes. What I'm trying to say is that a quantity will be called a vector only if, along with the fact that it has both magnitude and direction, like current, it will also obey the laws of vector addition, which current does not do. Okay? So, only if the quantity follows the law of vector addition, then we will call it a vector quantity. Yeah? Okay. So, this is the primary thing that you need to know, how to define a vector. It's not that the definition that we knew till now was wrong, it was only incomplete. So the complete definition of vector would be physical quantities that have both magnitude and direction and obey the laws of vector addition. Right? Now, a vector may be represented in two ways. There are two ways in which a vector can be represented. There is a geometrical representation, that is, geometrical means to draw a line. Okay? So, we have a straight line which has a tail and a head, arrow giving you the direction. The length of this line is the magnitude, okay, and the direction of the arrow is the direction in which the vector points. Okay. So suppose this blue arrow here This represents the vector A. I hope all of you can hear me and see the slide clearly. Yes?
Yes, ma'am.
Oh, thank you.
Yes, ma'am.
Because it is just one way talking, and sometimes very difficult to understand whether we are all together or not. Anyway, so this blue arrow here, let us suppose that it represents the vector A. So this length, the length of this line segment is the magnitude of the vector A, and the direction of the arrow will give us the direction of A. This is another vector which has definitely another direction and a different magnitude representing the vector B. Okay. So how do we add the two vectors, A plus B? Is it possible that we can add the two vectors? We know that vectors, what are vectors? Vectors are actually physical quantities, right? So physical quantities like force, it has a magnitude and a direction. So when more than one force is acting on a body, then we should be able to add up the forces to get the resultant force on the body, because that resultant force will decide in which direction the body is moving. So we must know how to add up vectors. Now this addition, is this addition the same as scalar addition, like we do algebraic addition, 2 plus 3 equal to 5, 6 plus 4 equal to 10, or is this addition something else? Obviously it is something else, because now not only the magnitude but the directions are also involved. Okay, so what we do is we draw the vector A as it is, and we bring the vector B. This is a sort of what should I say, usefulness of vectors, that you can parallelly displace vectors. I bring the vector B from here to here. I just parallelly displace it so that its magnitude and direction remain same, and there is no change to the vector. So I bring both the vectors in such a manner that A is there, and the end of vector B touches the one end of vector B, the tail of vector B touches the head of vector A. Okay, so they are forming two sides of a triangle. Then vector C that forms the third side of the triangle in the other direction. Okay, see, if you take the directions, then A and B are going in clockwise direction, but BC is in the other direction. Okay, not in the same clockwise direction, it is in the other direction. Then C is the sum of A and B. Alright. What about A minus B? We simply reverse the direction of B. This is A, we reverse the direction of B and we get minus B. This was B, we just take the arrow to the other side. So we get minus B. And again we join the two ends to form the triangle, and we get a new vector C prime, which is A minus. Okay. So this is the triangle rule of vector addition, and this is the geometrical representation of vectors. Okay, so geometrical representation basically helps us to visualize the vector. When a force is acting on a body, if I tell you it is a force of magnitude 10 newtons and acting in the northwest direction, then you can quickly draw a vector of say 10 centimeters length and draw it in the northwest direction. Okay, and you know that, okay, you can visualize the vector. This is how the force is acting. Now the other representation is called the component representation. Okay, earlier the first one was the geometrical representation. This is the component representation. What is the component representation? Now we draw the three axes. All of you know the coordinate axis. All of you have done a little bit of graph in your school level. So we have the three axes, X, Y, and Z axis, the Cartesian axis, which are perpendicular to each other and they meet at the point O, which we call the origin. And we draw the vector A, starting at the origin. Okay. So we have the vector A, of course. We are not creating it. The vector A is there. We draw our Cartesian axis in such a manner that the vector A starts from the origin of this coordinate system. So the tip of this vector, the point at which this vector ends, let us suppose that it has the coordinates A, AY, AZ. Okay? We know that any point in three-dimensional space has three coordinates, the x, y, and z coordinates. So the point at which this vector A ends has the coordinates A, AY, AZ. So A is a vector starting from the origin and terminating at the point A, AY, AZ. So the originating point is 0, 0, 0, and the terminating point is A, AY, AZ. Now what we do is we drop a perpendicular from the tip of the vector onto the xy plane. Okay. So the coordinates of this point is A, AY, 0. Perpendicular drops from the point A, AY, AZ to the xy plane at the point A, AY, Z. And then what we do is we draw perpendiculars from this point to the x and y axis and from this point to the z axis. Okay? So perpendiculars are dropped from AX, AY, 0 onto the x and y axis and they make intercept AX and AY respectively, and from this point on the z axis makes the intercept AZ. Alright. Now this angle that the vector A makes with the x-axis, let us call it alpha. Angle that it makes with the y-axis, let us call it beta. And the angle that it makes with the z-axis, let us call it gamma. So we can write, you can clearly see the picture, use your basic trigonometry knowledge, and you can see that we can write A equal to mod A cos alpha, where mod A is the magnitude of A. AY equal to mod A cos beta, and AZ equal to mod A cos gamma. Okay. This mod A, as I told you, is the magnitude of the vector. The cosines of the angles that the vector makes with the three axes, cos alpha, cos beta, and cos gamma, are called the direction cosines. Okay. From the direction cosine, we get the values of A, AY, and AZ, which are the Cartesian components of the vector A along the c-axis. Okay, so A, AY, and AZ are the Cartesian components. Just keep in mind that the statement Cartesian component is very important because we are working in the Cartesian coordinate system. We are in the x, y, z coordinate system, so that we can write the components A, K, Y, A, Z. There are other coordinate systems. You have done a little bit of polar coordinates in your +2 level. So you know that we can write the vector in terms of r and theta too. Okay, so then the components will be different. Only in the Cartesian system, these are the components along the three-axis x, y, z. Okay, and now the vector can be written as ax x cap plus ay y cap plus az z cap. Or we can also write I cap, j cap, and k cap in place of x cap, y cap, and z cap. What are x cap, y cap, and z cap? They are the unit vectors along the three coordinate axis in the Cartesian system. Okay, so this is the component representation of a vector in the Cartesian. All right, clear to everybody? So we can see that there are two types of expressions. Now, since we came across this term unit vector, let us see what a unit vector is. A unit vector is a vector in a given direction that has unit magnitude. Okay, a vector in a given direction which has unit magnitude is called a unit vector. How do we get a unit vector? We usually represent the unit vector like this: A hat equal to vector A divided by magnitude. Okay, so if the vector A is given and you are asked to find the unit vector, then you simply divide the vector by its magnitude. I hope all of you know how to calculate the magnitude, and you get the unit vector. In the Cartesian system, the unit vectors along the three axes are denoted by x cap, y cap, z cap, or I cap, j cap, k cap. All right, as you can see, each and everything that I'm saying or that you need to know are also written on the slide. So if you go back to the slide, you will be able to recap everything that is discussed in the class. Now, these unit vectors, I cap, j cap, k cap, or x cap, y cap, z cap, whichever way you represent it, they form a basis or a complete set of vectors in the three-dimensional Euclidean space. What does that mean? What do I mean when I say they form a complete set or a basis? It means that any vector can be
ম্যাম আপনার ভয়েস আসছে না।
Ma'am, your connection is too poor. You are not audible.
Excuse me, ma'am. Ma'am, your voice is not audible to us.
Ma'am, you are audible, ma'am.
Yes, that is because someone from your side has muted me. So all this while I was talking and you could not hear me because someone from your class had muted me. So which is why I kept on asking whether you can hear me. See, this is one thing in Skype that once I go to the screen share mode, I cannot see this screen. I can see only my PPT presentation. Same thing happens in Google Meet. Once I go to my presentation, I cannot see this screen. So I cannot see whether someone has muted me. And it is very unfortunate if someone has done it by mistake, it's all right. But if someone has done it purposely, then it's really unfortunate. Evening time, I'm sitting here trying to take an online class, and someone comes and mutes the speaker. So what is the point? If you don't want these classes to happen, then I am very